Welcome to Learn Chemistry Together. This video is about structural theory of matter. Imagine trying to build a modern house without blueprints, just dropping a pile of bricks, wood, and glass into a heap and hoping it functions like a home. In the early 19th century, that was essentially how chemists viewed molecules. Everything changed with a single radical breakthrough, the structural theory of matter. Today, we're going to look at how understanding atomic connectivity turned chemistry from magic into precise engineering. In the mid-19th century, three brilliant scientists, August Kekulé, Archibald Scott Couper, and Alexander Butlerov, working independently, laid the foundation for modern organic chemistry. Together, they proposed a revolutionary idea. Substances aren't just defined by their chemical ingredients. They are defined by the specific architectural arrangement of their atoms. Butlerov coined the term chemical structure and emphasized that physical and chemical properties depend directly on this arrangement. Kekulé introduced carbon chains and rings like benzene, while Couper developed early diagrams showing atom-to-atom linkages. Their combined work proved that molecules have fixed, three-dimensional geometry. So, how do these atomic buildings stay together? The structural theory gave us a simple rulebook based on valency. The predictable number of bonds an element can form. Think of valency as the number of hands an atom has to hold onto its neighbors. Carbon is tetravalent. It forms four covalent bonds. Carbon is the ultimate builder because it can branch out in four directions or form double and triple bonds. Nitrogen is trivalent. It forms three bonds. Oxygen is divalent. It forms two bonds. Hydrogen and halogens are monovalent. They form just one bond, serving as the outer caps of our molecular structures. By following these simple valency rules, chemists could suddenly predict whether a proposed molecule was chemically possible. To see why arrangement matters so much, look at these two molecules on the screen. Both share the exact same molecular formula. C2H6O, 2 carbons, 6 hydrogens, and 1 oxygen. On the left, we have dimethyl ether. The oxygen atom sits in the middle, splitting the carbons. It's a gas at room temperature with a boiling point of minus 23 degrees Celsius. On the right, we have ethanol drinking alcohol. Here, the carbons are bonded together and the oxygen is at the end. Its boiling point is 78.4 degrees Celsius, over 100 degrees higher. Same ingredients, vastly different properties. Molecules with the same formula but different atom connections are called constitutional isomers. Structure isn't just a detail, it completely changes reality. Let's look at how a single molecular formula C3H8O can represent entirely different chemical compounds depending on how its atoms are connected. These variations are called constitutional isomers. First, we have two alcohols where the oxygen is bound to a hydrogen atom to form an hydroxy group. On the left, one propanol places a hydroxyl group at the end of the three-carbon chain. Next to it, two propanol shift that same hydroxy group to the central carbon. Just changing the position of this group alters how these molecules behave. Finally, on the right, we have methoxyethane. Here, the oxygen isn't on the outside at all. It sits directly inside the carbon chain, splitting it into a methyl group and an ethyl group, making it an ether. A quick three-step solution determined valency 2. Connect high-valency backbone 3. Explore variations. Examples showing 1 propanol, 2 propanol, and methoxyethane for C3H8O. When you're tasked with finding all constitutional isomers for a formula like C3H8O, you just follow 3 simple steps. 1. Determine valency. Identify what each atom needs. C equals 4, O equals 2, H equals 1. 2. Connect high-valency atoms. Build your central chain with carbon and oxygen first, then cap the open slots with hydrogen. 3. Explore variations. Move atoms around to find every distinct connectivity, giving us 1 propanol, 2 propanol, and methoxyethane. To conclude, the structural theory of matter transformed chemistry from a mystery into an architect's blueprint. By recognizing that atoms follow strict bonding rules and form unique structural layouts, Kekulé, Couper, and Butlerov gave us the power to design modern medicine, materials, and life-saving technology. Thank you for watching, and please subscribe for more.